Okay, so this is Unit 3, Video 2, Part 2. We're just going to go through 2 examples. It shouldn't take too long, but I want to show you how to do these. Also, I'm going ahead and doing some harder examples so that you have these to reference, but don't worry, the problems will not start off this difficult. It's just to give you a kind of a frame of reference of where we're going and to kind of hit all the points that I want to hit. So in this problem, a ball is thrown upward from the top of a building at an angle of 30 degrees above the horizontal and with an initial speed of 20 meters per second. The point of release is 45 meters above the ground, and we're just going to deal with part A for right now, is how long does it take for the ball to hit the ground. So this is going to be similar to this problem where there's 2 parts, and I'll show you how we're going to break it up. So let's move on to the document camera here. And I have this set up for you. So this is example 1. Let's go ahead. This is what it looks like. It said that it was velocity was 20 meters per second at an angle of 30 degrees above the horizontal and the top of a 45 meter high building. The first thing you're going to do is draw this picture. And then I always kind of draw like a prediction of what the motion's going to look like. And then I make my X, Y, T chart. And that's the most important part so we can separate these variables. So what we're going to do is the first part is to figure out, let's see, we have the initial velocity given and we can draw the components of the initial velocity. So this would be v naught x and this would be v naught y. And so we can solve that since we have an angle and we have the hypotenuse, we can use our SOHCAHTOA and solve for this. So for the x direction, it would be cosine. So it's going to be cosine 30 times 20. And you'll notice that this will kind of become habit. So cosine 30 times 20 is going to give us, let's see, I have my calculator, is 17.32. And so I go ahead and I put it in my chart under the x direction. For the y direction, it's going to be the same process except for it's going to be sine instead of cosine. So it's going to be 20 sine 30. So 20 sine 30 comes out to 10. And so my initial velocity in the y is 10 meters per second. Now let's figure out what else we know about this. The first thing I would do is make sure that those are both positive, which you can check by saying, okay, I'm going up, so the y direction should be positive, and I'm going to the right, so the x direction should be positive. We also know the acceleration, because it's always going to be the same. So in the x direction, we have 0. Remember, there's no acceleration in the x. And in the y direction, we have gravity. So it's negative 9.8 meters per second squared. And don't forget that negative sign. So far, that's all they've given us. And so we're going to use this kind of special trick. We're going to break this thing up into 2 pieces. We're going to break it up into the top half and the bottom half. We're looking for the total time. So that's important to make sure you know what you're looking for. So in this first top part, this is all the information we know. Remember I said before that you have to have 3 variables to solve for another. We can only work in this column or this column. We cannot mix the 2 of these. And so we need 3 in one of these columns. So what I would suggest is we know some information about this top part. We know that at the top in the y direction only, the velocity stops because it goes from being positive and then it's going to turn around and go negative. So in between that, it has to stop. So the final velocity in the y direction is 0 at that top point. So I would go ahead and plug that in. And all that means is that everything we know that we can find out from these numbers is only going to be from here to here. So we just have to keep that in mind. So I would figure out the time it takes to get to the top of here. Might as well start with time because that's what we need. I'm going to go to my equations and find out which variables I have. So let's see, I have these 4. I'm not looking at D at all, no displacement. So I think we would need the one that has no displacement. So that's the second one. So the equation is VF equals V naught plus AT. We can plug in only using the y. So 0 equals 10 plus negative 9.8 t. And then we can subtract 10 and solve for t. And we would get 1.02 seconds. So that's the time it takes to get from where we started to this point, because that's where we're using information for. Now the nice thing about projectile motion is it's symmetrical. So to get from here to here is 1.02. So to get from here back to that same height again, so back to that same line that matches from where we started, it's going to take the same amount of time, so 1.02. So here, from the total time for the top part is 2.04 seconds if we add those up. So that's really nice to know. So now all we need is from here down to the bottom. So I would suggest making a new chart just because there's going to be new information in it since we're looking at two different places. So the initial velocity in the x is always the same because there's no acceleration, so we can assume that stays the same. The acceleration is 0, right? In the y direction, the velocity is not the same, but there is a special thing that we note because these are symmetrical, and because in the beginning this velocity was positive 10, and now at the same height, we're going to have the same velocity, but now it's going down. So we're looking at this vector here. And so the y direction of that vector is the exact opposite of this one over here. So these two are opposites. So this is going to be negative 10, and that's only because it's at the same height as it was over here. Otherwise, that would not work out. So we can use our initial velocity now from here down to here is negative 10. We know the acceleration will never change. It's negative 9.8. And we have one more piece, this 45, that will help us out because that's 45 is from here down to here. And when we're going from here down to here, our displacement in the y direction is negative 10 because we're falling negative 45. We're falling negative 45 meters. So we can put our displacement here as negative 45 meters. And now all this information is representative of starting here and ending down here. And so we have three things. We're looking for time. Remember, we want the total time. So we look for, let's see, no final velocity in that list. So we can't have any final velocity here. And so let's see, the only one would be this one. So that equation is d equals v naught t plus 1/2 at squared. So we plug in, only in the y direction, remember. So we have negative 45. Make sure you make that negative because you're falling down. Okay, be careful with that. Equals negative 10t plus 1/2 negative 9.8 t squared. If we kind of simplify this thing out, this is negative 10t minus 4.9 t squared. And you notice that we are now stuck in a quadratic formula situation. Here, we have too many t's. So if you have a program in your calculator, that's great. Otherwise, you can just solve it the a normal quadratic formula way. The other option is to find the final velocity first using a different equation and then plug into this one or a different one. It's kind of up to you. I'm going to just go ahead and use the quadratic formula the old-fashioned way. And I've already done this, and so I'll just give you the answers I came up with. So t, not x, t is either negative 4.22 seconds or 2.18 seconds. And so it should be obvious that negative time doesn't make any sense, and so we have to go with the second answer. So then the total time would be the 2.04 from the first half plus the 2.18 from the second half, and you end up with 4.22 seconds. So that's part A.
Okay, so part 2 or part B asks us to figure out the final speed as it approaches the ground. So we talk about right before it hits the ground. So we're kind of talking about like this moment right here. And so since velocity is a vector, we need to figure out the two components. So we need the y component of the velocity and we need the x component of the velocity. So the easy part is that the x component of the velocity, since the x direction has no acceleration up here, the initial velocity in the x and the final velocity in the x will always be the same. So we can fill that in. So we know the final velocity is going to be 17.32 in the x. Now for the y, I would use just from here down, because it doesn't really matter if we start from here or up here. As long as we know a lot of information about here down to here, we can figure out the final velocity in the y direction down here. So that would take us to this list that we had. So let's go ahead and figure out what the final velocity would be there. So we have the initial velocity is negative 10, we have the acceleration, we have the displacement, we know the times. We have everything, so we could just use the easiest equation. So in my opinion, that would be this one. And so if we go ahead and plug into that one, we get VF equals negative 10 plus negative 9.8 times, and then the t that we found for that section was 2.18. And so if we plug that into our calculator, we would get VF equals negative 31.36 meters per second. So now that we have both pieces, we basically, if we blow up that final velocity vector, it looks something like that. We have the y direction in negative 31.36, and we have the x direction at 17.32. And so we can just Pythagorean theorem to get the hypotenuse, to get the final velocity. So let's do that. And so if we do that, we get this to be 35.83 meters per second. So the final velocity of the whole thing is 35.83 meters per second, and then we need direction. So I usually just find this angle here, theta, and so we can do inverse tan of opposite, so 17.32 over adjacent, so 31.36. Don't worry about the negative sign. If we just ignore the negative, it'll just give us this angle. If we use the negative, it's going to take us around and find that whole angle. So we can just use this positive. So then inverse tan of 17.32 divided by 31.36 gives us 28.9 degrees. So our final answer is at 28.9 degrees. And I would say that this is, if this were my north, east, west, south, I would say that then that's 28.9 degrees east of south. So this is my final answer for part B. Okay, so then let's move on to part C.
Okay, so then part C asks us to find the horizontal range, which is really just the displacement in the x direction. So we're really just trying to find, right, this distance here. That's the range. So we can just plug in. We have enough information about x. We know the total time. So if we fill in this table, we know the time is 4.22 from our first part. So we have enough information. So I would suggest using this equation. So it's the d equals v naught t plus 1/2 at squared. I would use that one just because in the x direction there's no acceleration, so that means that this is 0. So 0 multiplied by all this makes this go away. And then we can just go ahead and plug in for displacement. So v naught was 17.32 and the total time was 4.22. And so if we calculate that, we get our total distance, or our total range and the displacement in the x to be 73.1 meters. And that's it. So that's the end of example 1. Let's go ahead and start example 2. So let me bring it up and show it to you what that looks like. So example 2 says a jet plane traveling horizontally at 1 × 10⁻², so 100 meters per second, drops a rocket from a considerable height. The rocket immediately fires its engines, accelerating at 20 meters per second squared in the x direction while falling under the influence of gravity in the y direction. When the rocket has fallen 1 kilometer, find its velocity in the y direction, and we'll do each part separately. So we're going to find its velocity in the y direction. Okay, so here's the setup. This is my jet plane. I don't have a very good drawing. And here's my rocket. It's attached, so they're both traveling 100 meters per second to begin with in the x direction. And then the jet plane is going to release the rocket, and immediately after release, the rocket is going to have an acceleration of 20 meters per second squared in the x direction. So here's how I set it up. So this is the stuff I know so far. Initial velocity in the x direction for the rocket was 100 because it was attached to the jet plane. The acceleration immediately when it was ejected was 20 meters per second squared in the x direction. In the y direction, since this velocity was in the x direction, there's no proof of any velocity in the y. The velocity in the y is 0. Acceleration of gravity is negative 9.8. And then it says that it's going to fall 1 kilometer, so that's 1,000 meters. And we want to find out how fast is the rocket going in the y direction, the velocity in the y direction, after it's fallen this distance. So this is the information we have. We have 3 things in the y direction, so we can go ahead and solve for that final velocity in the y. So we don't have time, so I'm going to go ahead and use this one. And if we plug in, we're going to have VF squared equals 0 plus 2 times negative 9.8 times negative 1,000. Make sure you make that a negative 1,000 because you're falling down. And then 2 times 9.8 times negative 1,000 gives us VF squared equals positive because of the 2 negatives. So 19,600, and then we take the square root of that. And so our final velocity in the y direction is 140 meters per second. Make sure you put a negative because it still is falling down. And since we took the square root, your math won't actually know if it's negative or not. So that's part A. Part B asks us once it's fallen 1 kilometer, what is its velocity in the x direction? So we need the v final in the x. Now, we don't have enough information in the x direction. So this is where this nice little trick comes in. The only thing that's the same in the x direction and the y direction when it's falling is the time. So if we can find the time in the y direction, we can put it over in the x direction because time doesn't have any direction. So if we find it over here, maybe we can use this nice easy equation. Now that we know all this information, so this is part B. So VF is negative 140, V initial was 0, A is negative 9.8, and we have T. So if we just divide by negative 9.8, we get that T equals 14.29 seconds for it to fall that 1,000 meters and for it to change its velocity here. And so we can move that to the y direction. The x direction. And now since we have time, we can find the final velocity in the x direction using, let's see, we don't have delta x. So we have to use that first equation again. So VF equals V naught plus AT. Now I'm using all this stuff in the x. Remember, I can't mix except for the time. So VF is what we're looking for. V naught was 100. Acceleration is 20. And time is 14.29. So if I do that math, I end up with VF equals, actually you guys can see this, 385.8 meters per second for the final velocity in the x direction. So that's part B. And then part C says to find the magnitude and direction of its velocity. So basically just its overall. So we have the x, we have the y, and this is kind of a interesting piece now. And we want the overall. So remember this rocket is like accelerating this way and it's also accelerating down. So when it's coming down, it's actually kind of coming down with like a velocity in this angle. So we have a velocity in the x of 385.8. We have a velocity in the y, and this is where the vectors come in, of negative 140. The negative doesn't really matter when you put it in here for Pythagorean theorem, but it's okay, you can add it in there if you want. And then so our final velocity total would be here. So we just use our Pythagorean theorem to find this one. So I'm going to square the 385.8. I'm going to add that to 140 squared, and I'm going to take the square root. So I get my V final equals 410.42 meters per second. And then we just need direction. So I would probably just find this angle here. And you never really want to find this angle because it's not a reference angle. You want to go from like the x, where you can picture the x-axis kind of. So this is my x-axis. I can find this angle, and I can do it by doing like inverse of tan because I have the opposite in my adjacent side. So I can do tan, let me move this so you can see it. I can do tan inverse of opposite, which is 140. You can still ignore the negative sign for now. Over the adjacent, and that'll be my angle. So if I plug that into my calculator, make sure you're in degrees, and I am in degrees. So I take the inverse of tan of 140 divided by 385.8, and I get theta equals 19.9 degrees. So my final answer for my velocity would be V final equals 410.42 meters per second at 19.9 degrees. And I would say that this is south. If this was east, right, and this is south, then this is going to be, this angle is south of east. So south of east. Or you could say below the positive x-axis. So that's part C. Okay? So make sure you write down any questions that you have on that. And I believe this takes us to the end of our video for video 2. So that's it. And then just make sure you write your questions down in that Google Doc on Moodle. And we'll go ahead and practice some of these problems in class next time. So let's go ahead and set this up. So we're going to go ahead and do this in part 2. So go ahead and move to part 2 of the video. Okay, so here's the setup, right? So we have some kind of jet plane. It's going to drop a rocket. I know this is a terrible drawing, but that's okay. So it drops this rocket, and it tells us that the initial velocity is 100 meters per second horizontally. So that means that in the x direction, and we'll go ahead and start on part 2 in a bit.